Hello everybody, good morning. My name is Wolfgang Maas. I'm going to present a paper that I've written together with Vida Story about bridging or pairing conceptual modeling with machine learning. Conceptual modeling and machine learning are fields that both try to find structures. In conceptual modeling, as we have seen right now, these structures are obviously conceptual, while in the case of machine learning, these structures are sometimes conceptual, based on the given attributes that we use and the underlying concepts, but sometimes they are also pre-conceptual and even subconceptual. Yeah? Because the word conceptual appears in both directions, it should not be surprising that conceptual modeling and machine learning have many things in common. In this paper, Vida and I have compiled and discussed what conceptual modeling can contribute to machine learning and vice versa. The details of the paper are probably much richer than what I'm going to present here, but I give you an overview of the argumentation in both directions. Okay, so first we take the trip from conceptual modeling to machine learning to see how conceptual modeling can contribute to machine learning. And then in a second part, which is a little bit an overview of very many techniques that we could leverage in order to enrich conceptual modeling by the use of machine learning. The first direction from conceptual modeling to machine learning, the role is descriptive and forms a data scientist. The standard data scientist uses tabular data with very atomistic features, yeah? And the rich structure that is underlying those kind of features is usually not very explicit, not very transparent. So one way is to be descriptive, that conceptual modeling can describe to a data scientist what the meaning is of these particular data features or attributes, as we might call it in conceptual modeling. But also there is a computational side in order to embed conceptual modeling into data analytical implementations. Yeah? So I think these are the two separate dimensions that we might distinguish. In the other direction as well, yeah? I mean, if I have a lot of data and I analyze the data with the help of data analytical processes, be it supervised learning, be it unsupervised learning, which is more exploratory, this might inform a conceptual modeler. Where are the holes in my conceptual models? Where maybe also some discrepancies between concepts. So enrich also the understanding of the conceptual modeler by the use of data analytics. But also here, there is a potential for research doing that on the computational level. How to merge both fields, yeah? The techniques that we see in conceptual model, merge that into kind of transformation as we have just seen right now. Yeah? How can we make use of that? Good. So the underlying thinking here is kind of a triangle that we start from. Yeah, I will not go into details, but I think it should be very familiar to all of us that we have some mental models that we try to express in form of conceptual models in order to communicate and share knowledge. And this is somehow anchored in some worlds. Yeah, it could be physical, maybe it could be also idealistic. But in many cases, like in Industry 4.0 kind of application, healthcare and all these kind of domains that we have some physical background. And now, by adding the world of data, it used to be very straightforward because the data is included into information systems. But now we are not only merging that in the direction of conceptual model, as we are all used to in our community, but it's also directly used in software models. And on the next slide, we see that there are some question marks, how we can deal with the data sphere, how to integrate that into machine learning. I mean, that's pretty clear. But how do we use what the data scientist uses, the data models, how this relates to the conceptual models? At the moment, it is a question mark. A normal data scientist normally doesn't care. So we need to bridge that, and also the question about how can we use conceptual models in order to inform the work on the artificial intelligence side, building systems, so that the quality of those kind of systems might be improved. We have presented an extension of what a data science development cycle. I briefly go over that, but first, problem understanding. I think here our community has a lot to say about that, how to formalize that. Then what in data science is pretty straightforward is data collection, data engineering. But data engineering and extracting features is a very syntactic kind of work in many cases. I will show an example where we can also add semantics to that kind of process. Then you do model training, model optimization, and then you integrate that in some information system in order to support analytical decision-making, data-driven decision-making. Just as a brief primer, because not everybody might do a lot of work in the area of machine learning, but when you look into data scientists, what we all learned in school is the descriptive side of statistics, to describe that, but data science is also looking forward, exploratory, predictive analytics, but what the goal is also prescriptive, goal-oriented kind of recommendations. Another field is simulation. This is a very new kind of field. And generative analytics is that we create artificial data spaces on which we can work on, which is in particular important if you think about privacy issues, that you work with healthcare data. You cannot work on the data as such, but you are better off, or that's one way how to do it, to generate your own data. Okay, here are some techniques. Sequential models, as we know that, even with time series data, image models, two-dimensional, three-dimensional models, generative adversarial networks, and all the things about encoding, encoding of domains in some vector spaces, and that you can work with that. Always, the key element of anything what you do in machine learning is to find some gradients. I mean, that's a typical way in order to do the adjustments. And therefore, the underlying machine is in contrast to what we are used to in conceptual modeling, where we do logical kind of reasoning. This is mainly statistical and differential equation calculus based. Okay, so now let's jump into it from conceptual modeling. How can we support machine learning? In machine learning projects or research, we face very very issues. And now I would say that data science is becoming more mature by accepting those kind of issues, like imbalanced data sets and biases. Biases that are only understandable if you know the semantics that is lying behind the data. Otherwise, in many cases, you cannot judge the biases. On the model side, overfitting and underfitting is always a big issue. Underfitting means the model is too simple. It cannot capture the signal and the functionality of the data. And overfitting means you have a huge deep learning model and you have sparse data, and it trains exactly to these simple data, and then it doesn't cope well with new data. And what we did is we compiled, on one hand side, the logic that I've shown you with the data science development process. And then we have seen on the right-hand side, we try to find models and approaches from the conceptual modeling community that might build bridges, that might inform the left-hand side. Yeah? For instance, if you do data collection, all the things that we know about data requirements and data quality should be brought in order to make sure that the data has a certain quality, that it fulfills certain kind of requirements. This requires also ontological logic about the domain, so that you can make sure the data is what it is supposed to do. Here is an example. It's a very famous data set of some tribes in the US, and they have some diabetes issues. Data is available online about diabetes. And if you look at the features, the blue parts here are the single attributes, we would say, that you bring in. And then when you apply statistics on that, you get certain kind of results. A normal data scientist would, I mean, I'm playing here, let's say, a card that is maybe too coarse, yeah, but a normal data scientist would say, I don't care about the semantics of the data as long as the accuracy is good enough. Yeah, and that's kind of an issue that that I would like to express in the following slides. For instance, if you have here the minimum values of some of the features, we see that the red part, 0, would be, from a biological perspective, obviously quite difficult. Yeah, if you have a 0 pulse or blood pressure, you might be dead. Yeah, so obviously this data is not really helpful. You have to fix the kind of data. But on the other hand side, we see some values that make sense. I'm coming back to that. The next step is what we see that we can introduce is the ontological representations also to annotate the data. For instance, here by the help of SNOMED representation or ontology, where it is obviously also a point where we would like to automize this mapping into this data set. Yeah, I mean, which concept is related to which kind of feature? That would definitely help. And then if you can do that, you can also do some reasoning on that. For instance, concept alignment, I just said, but also concept similarity measures and semantic distances. Which kinds of concepts are similar and might relate to some features that are not considered yet? Yeah, there might be somewhere this kind of data might be available somewhere, but it's not considered that. So if you move up the ontological path, yeah, to superclasses, yeah, even in this taxonomic relations, you might find ideas, or maybe also automatically, you might identify features that you would like to test also in your model. Okay, so here is an example, yeah, that you say, okay, down here we have leads 2. Obviously, it's semantically not very related to has demography, but if you go up here, you have at least 3 or 4 concepts that you could put to a test whether they are informative. Okay, back to our data. The zeros we already have seen with blood pressure. You might have a very simple theory behind that 0 blood pressure is not very healthy, but also glucose. Yeah, I mean, you see on Kaggle, you see several notebooks that take the data right away. Okay, but if you take glucose, and when I looked at that, I was a little bit confused about that, because diabetes starts when you have a certain level of milligram of glucose, 200. And I couldn't find anything with 200 plus. Yeah, so diabetes, and a strong indicator for diabetes, was not part of this. And then I did some analysis on the data, and I found out, okay, there is a cut. Yeah, there's a cut that is not explainable. Then I looked in the paper, and there was a footnote which said, yeah, we cut off the data with 200 plus. Yeah, we simply cut that away. So obviously, we have a hole here in the data representation that is only understandable if you know that glucose values above 200 are kind of indicative for diabetes. Yeah, then you go back into the domain and say, okay, where is the rest of the data? Otherwise, it is clear that the accuracy will not be very high. Okay, so another thing is adding data constraints. If you have here extremely simple conceptual model, obviously, yeah, but if you have data constraints with OCL, yeah, you could say glucose of a person cannot be 0 or negative. Then patient's age between 15 and 120, 15 maybe due to ethical reasons, and then also that you say glucose levels above 200 are related to diabetes. That's something we are used to. And then you can check that with your data and you realize, okay, the first constraint is not fulfilled, the second is, and the third we don't know. Yeah, the data is not giving us information. That would be helpful for a data scientist, definitely. Then somebody came up with a very interesting idea. I think that is also informative to say, okay, I take the data that is available in the data set, but I work with the data. And working with the data requires certain kind of understanding what the data means. And in this case, this guy said, okay, I want to add a new data field, a new feature to my data, and this is processed. Namely, if the age is lower than 30 and the glucose level is smaller than 120, I give that simply a 1, otherwise a 0. Yeah? This is very simple. Yeah? And the same thing here if the person is also young and pregnancy lower than 6. Yeah? I mean, still a big number, but simply only adding a 1. And what you see then, with this simple semantics added, you see that the accuracy of this model is, and precision recall is jumping up by 20%. For us, it's simple, yeah, but the impact on the model is huge. Okay, that was just highlighting a little bit about what conceptual model could bring in. The other direction, from machine learning to conceptual modeling, there are very many models that we could leverage in all regards. Yeah? And this market of models that we could leverage is exploding, actually. So we have general supervised learning, we have sequence learning, generative learning, graph learning, unsupervised learning for exploratory kind of investigation, and reinforcement learning as in a very early stage. But everything that is related to unsupervised learning is quite developed. Then we have a lot of techniques from text mining that we already leverage in our community. Rule mining, anomaly detection also. I don't have the time to go into all the details, but please contact me if you need information about that, yeah, that I could potentially answer. What's also a very interesting field is explainable AI, which already is designed as being a bridge from data and data analytics to the conceptual level. It's still on a very low level. Yeah? It says which features are more important. But slowly it is also trying to extract more conceptual relationships. Yeah? For instance, like the relationship between, I can't barely see that, bad and good and not. Yeah? Okay, so not so good. Yeah? It's in the text. Okay, so it's not just one feature, these are two features if you have it one hot encoded, and you say, okay, there is a kind of relationship. Knowledge graphs is already giving us something in that direction. Yeah, you might know that here in the right corner, you see the original data space. Here it's only two-dimensional, and what you do is an encoding in some vector space. Usually lower dimensional vector space. Yeah, I come from, let's say, 50 features, 100 features, and I try to find a lower dimensional space that I can project this data into. And in this lower dimensional space, I use distances in order to measure similarities between those kind of items. All this in knowledge graphs is mainly on instance level. Yeah, it is something that informs us, and we could use that on the conceptual modeling side in order to build on that. What does it mean? Yeah, what kind of concepts are there? Does it support super concept taxonomic relationships? Yeah, subsumption relationships. Okay, another one that stems from social network analysis. You can simply look at the data in an encoded vector space and say, okay, what is central, yeah, and what are communities, kind of clusters, connectivity between clusters, node similarities, when you have these clusters, how similar are they? This is in particular used for machine translation. Yeah? T&E representations are used in order to see similarities between languages, like Korean languages and language and Japanese language. Yeah, French and German. Yeah, there you see strong similarities if you find the right encoding. And this is quite helpful in order to understand the conceptual relationships. So in summary, very briefly, before I come to my outlook slide, in both directions, I think we have presented in the paper some possibilities, or I would say many possibilities, where conceptual modeling can help machine learning, but also where machine learning can be embedded in our research on conceptual modeling. An outlook, what is not in the paper, what I would see is operationalization of building trust in conceptual models. Yeah, this is something where machine learning could potentially help us. Yeah, so kind of symbol grounding in data. Yeah, so we have the conceptual models, and then we say, how is it anchored in data? But also conceptual model provides semantics to data that might increase the trust in black boxes or gray boxes. Yeah, so this is how we could add to trust in machine learning. Data drifts is a very important topic because in conceptual modeling we might tend to the situation that the world is stable. In data science, we know the world is very unstable and concepts shift. Yeah, the data shifts and therefore also the meaning of the features and the relationships and the overall model moves. And the same holds for relationships. And I think that is a very important kind of direction we have to investigate more. Then modeling dynamic systems. I'm working a lot with a dynamic system in mechanical engineering and simulations of milling processes where we work a lot with differential equations. How I can include that into conceptual modeling is some of the works we are currently doing. And this is even increased in complexity if we try to model what we are doing there with quantum services and quantum machine learning. What we are doing right now in the project, we have no possibility at the moment to include conceptual modeling in this kind of models when we try to model differential equations and the representation even in quantum machine learning representations and quantum computing representations. So I think there is a huge gap we are looking at in the future, and this is a very tiny little step for that. Thank you very much.
Well, thank you very much, Wolfgang. You know that this topic is a challenging, a fascinating one, and we have been talking about it in the past. I have a very short question that is related to the panel that we had the other day, where we were discussing or remembering the distinction between data and information and knowledge, and so data engineering is not information engineering or information system engineering. So, well, the question is, if how to answer the question of when a machine learning contribution or a paper that is normally sent to a machine learning conference could be sent to the CAiSE audience because it could be seen as an information system engineering contribution. When a machine learning contribution is what can be perfectly argued to be seen as an information system engineering contribution, and I think this is part of my answer. I don't want to bias you with my answer, but conceptual modeling and the connection that you made between data science and conceptual modeling is just a kind of framework where you should be able to identify what kind of new idea that is a significant idea for the information system engineering community is in this machine learning oriented research contribution. You know what I mean?
So you mean how much shall be integrated in this community?
No. When, for instance, your paper is a machine learning paper, that could be perfectly sent either to the CAiSE conference,
yes.
the ER conference. So the question is when a paper that is machine learning oriented people, what kind of material is susceptible to be sent to CAiSE, because it's valuable for the information system engineering community.
Oscar is asking, how can we attract machine learning people to CAiSE?
Sorry?
Oscar is asking, how can we attract machine learning people to publish here?
I mean, my PhD students, they only know 3 or 4 conferences. NIPS, ICML, and some of the smaller ones. Yeah, ICHCAI, ECAI, yeah. These are the conferences. The computer science people, they have a very thin area where they accept, they want to get into those kind of conferences. Yeah, I'm more reluctant with that, yeah, and I try to tell them, okay, we do that with IS. But I tell you a story. We did some work on EPO, on doping. Yeah, we investigated whether we can predict whether there is doping with EPO or whether there is urine sample swapping. We submitted that to IS conferences several times, and we got rejected because they said, first, it is too technical, and second, it is too much in the domain of biology. So I think if we want to integrate such kind of research, maybe we have to open up a little bit, yeah, to give them a home and say, yes, you are welcome, yeah, to present your work, maybe with a different spin. Definitely more with what is the contribution to conceptual modeling, yeah, definitely, yeah. But my perception is we have to open up, yeah. This work, what I just said, we submitted to an IEEE conference, fully accept. All 3 reviewers said, great work, great work, great work. IS community said 0, 0, 0. Yeah, so this is where we are. Yeah, and I think this is where we have to ask ourselves. Yeah, do we want to be open for that kind of research? I mean, it's only my example. I don't know whether other people have similar experiences.
One stupid question. It's a very nice slogan. Anything on its place. Let's say you can eat a soup with a spoon or with a knife. Sometimes you succeed with a knife, maybe, if you are very successful. Do you have a demarcation criterion when not to use a conceptual model?
Who should not use conceptual model?
For instance, in these processes, you don't need all the time a conceptual model behind. You have some analysis, and then you say, okay, fine, these are results. I do not have to conceptualize it.
I mean, conceptualization is innate to any kind of data science project. Yeah, I mean, you somehow have to interpret what you have found. So what we see is that anybody who is working with data has some underlying assumptions. The problem in data science is oftentimes these assumptions are not made explicit. So everybody is looking at the metrics at the end and say accuracy 99%, 80%. Oh, great! Yeah, we trust that. And later on, we realize that there were some problems with the underlying assumptions of a data scientist who is not a domain expert. And this person cannot make explicit why this data is used in that way, why missing values are used on the medium, by a median or by a mean value, and all these kind of things. They are implicit. Yeah, so I would say there is always conceptual modeling, but oftentimes it's simply implicit.
Very interesting work. I'm wondering about the other examples of combination of conceptual models with machine learning, because the example that you gave us on the diabetes problem was more on like working on the data itself.
Yes.
But I'm wondering if you have also good examples of a combination of conceptual models and machine learning techniques to come up with the answers regarding the problem that...
Sure. I mean, that was the restriction of this paper, yeah, to have not to have a fully elaborated machine learning model that can contribute. But I think this example about encoding into vector spaces and seeing relationships. Yeah, this is something that can be right away integrated in link prediction for predicting relationships between concepts, and then to check, okay, is it supporting this or is it not? Yeah, I mean, we a couple of years ago we have 2 papers, one at Higgs and one at ER conference, where we went in that kind of direction, worked pretty well under certain kind of conditions. Yeah, there you can support the model that has been found and say, yes, I have data support, data analytics support for this model. I think that is already a first step. But then the next step will be creating a certain kind of relationships. At the moment, knowledge graphs that you see, 80–90% of the representations and the relationships are crap, yeah, useless. Yeah, and there I think we can work together and say, okay, can we bring in ontologies? How do we overlay that? Yeah, superimpose that. Open, very interesting kind of research, I would say.
Thank you very much.
You're welcome.